So the next steps, I guess, for anybody, if you're interested, is being curious about water, and in particular is the main fluid that I deal with. And when you're running models, you need to know that they are doing the right thing. And so I would recommend trying to model things. There's a lot of test cases in OpenFOAM. There's lots of good tutorials, and some of those are things you might be familiar with, and so you can run those if you are aware. But the other thing that is very useful is modelling things that you know what the answer already is, so you know whether then the software is doing the right thing. And here's an example of something I'm familiar with, is pouring some milk out of a carton and seeing if I can get into the glass or not. But here's an example of something I know what the answer should be, and so I'm able to model it, and it tells me whether I've got the right answer or not. So with all engineering problems, it's always handy to know what the answer is roughly before you start, and so then you can work towards using the model as a tool to help work out whether if I have a hole in my carton, whether that's going to the milk's going to come out faster or it's going to glug or not into the glass or not. So these are some examples of things that you can do with OpenFOAM.
Hello and welcome to today's webinar covering 3D CFD modeling with a special emphasis on the open source program OpenFOAM. I'm your host, Craig Price with the International Water Training Institute. On behalf of the Australian Water School, we're pleased to welcome almost 1,000 attendees from right around the world. So let's welcome today our expert presenters, Ray Shi, Colin Terry, and our panelist, Kyle Thompson. Let's have a brief introduction from you before we dive into any of the technical content. And let's hear basically first where you're coming to us from today, and let us know also how long you have been in the CFD business. So let's start with Ray.
Hi, my name is Ray. I'm a hydrologist based in Perth. So I picked up CFD when I was doing my PhD. It has been like 3 or 4 years, I think. 4 or 5 years, probably. Yeah.
Excellent. So he's, Ray's just right down the street from me here. So from the west end of Australia, let's go over now to the east side. Colin, where are you coming to us from this morning?
Hi, Craig. Yeah, coming from nice wintry Hobart in the southern part of Australia, in Tasmania. And I've been involved in hydraulics for over 3 decades, but more CFD for the last 4 or 5 years. So enjoying coming to things a little more freshly, but doing other things that are related to it, building up to this point.
Perfect. I hear you can see Antarctica from your house, I think.
Pretty much. It's one foot in one step, one into the snow, basically. But it's just more lots of rain, enjoying the nice sort of burst of winter rain, which is our Downs love.
Excellent. Kyle, familiar face with us here today. Good morning. Where are you coming to us from today, and how long have you been running CFD models?
Craig, coming from a slightly chilly Gold Coast. So when I moved down here, everyone promised warm beaches, but it's not so warm at the moment. Quite a summer. But I've been doing CFD for almost a decade now. I started off originally, I guess you would say, investigating bridge failures. I wouldn't say auditing, because back then no one was really doing CFD for bridges. Maybe TMR and US Federal Highways Administration were doing some modeling, but no one really knew if it was beneficial or not. I had quite a few bridges I was looking at in HECRAS 1D and 2D that were failing, and I couldn't get the shear stresses and velocities and things out of the 2D model to replicate the material that moved in those failures. So hence I started going down the CFD path and started working out some useful things and learning lots of things.
Perfect. Well, what we'll see here in the background is the poll results from the audience, and I'll compare this a little bit to some of our previous webinars and see if we've got any increase in CFD use. As typical, we've got most of our attendees from commercial and consulting. Interesting that 2D is leading the way over 1D. 1D is kind of falling a little bit out of fashion, I think. 3D is picking up a bit. That's not really all that much higher than one of these things we had a few years ago, but it depends if we add up both of these types of 3D modeling. If you're not familiar with 3D shallow water equations versus 3D CFD, we will touch on that today during the webinar presentations. And it looks like on the applications, we're pretty much spread right across the board. I'm surprised to see stormwater infrastructure come up so high. Colin, I think you've been using CFD for all of these applications. Any surprises there with the poll results?
No, you sound like you're calling a race, a horse race there with a different 1D versus 2D, but definitely things change over the years as we've been doing hydraulics, and more computing power is giving people the options of doing more 2D work, I guess, and that's great to see, I suppose. It's sometimes much easier, as we know, to do the 2D than the 1D in some of these cases anyway.
Yeah, exactly. Okay, so how this is going to work today, I'm going to just start out and provide some additional resources right at the beginning. Sometimes I provide these at the end, but I thought I'd just throw this out at the beginning so you can see that there's a ton of content we could put out there. We'll pack as much as we can into this 60-minute session, but I'm going to continue to post additional resources for you here at this webpage called hydroschool.org/CFD. And so I'll step through this briefly, and then Ray and Colin will present some of the intricacies and considerations for modeling in 3D CFD, particularly with a focus on OpenFOAM. Kyle will be in the background answering your questions. The other presenters, when one is presenting, the other will be answering questions as well. And then we'll all come back on for a live panel discussion where we will address those questions that have been upvoted the most. So on this website here, I will post the recording link here as well to the to today's session for those watching this on YouTube later on. Keep in mind, we will have some upcoming courses. In September, we're going to have a course where we step through some specific examples. You will get to do this yourself if you want to sign up for this course. Do subscribe to the Australian Water School channel so that you can be notified when the course is made live. That'll be coming to you in the next few months. And we do have some Flow 3D training, some webinars and courses coming up as well later this year. If you are brand new to 3D CFD, you may want to have a look at our webinar number 91. Australian Water Schools webinars are numbered, and so you can always go back to the channel and find these ones. We did talk here about the differences between coastal circulation models, what we're calling far field models in that webinar, and then the near field, hydraulic structures. That was with Alden Labs and Flow 3D participating as well. We do have a course that's available for you if you want to get into the principles of 1D versus 2D versus 3D. There's an on-demand course available to register for right now and complete at your own pace. That is part of our Hydrology and Hydraulics Essentials series, and that can be registered for using the links that we've got here. Now, I've posted a few selected ones. We've mentioned 3D and CFD modeling in many of our previous Australian Water School webinars. Here are a few that I've picked out. Rock scour with Flow 3D. We've got 3D coastal modeling, in this case with 2Flow. FV, I believe, was what was covered in this one. We did talk about the advantages and disadvantages of 1D versus 2D versus 3D on hydraulic structures, including culverts and spillways in this webinar here, number 63. With bridge scour, likewise, we talked about all the differences and trade-offs in those applications. We have fish passage. Kyle helped us out with a couple of fish passage webinars, number 1 and number 2. Number 1 was international fish passage. Number 2 was the fish that can't jump quite as high here in Australia. And we showed physical models and 3D CFD models of those. And this one was really fun. There's a 3D CFD model of some of the individual structures for different wave parks and whitewater rafting parks and things like that. So we showed a few there. There are some additional resources that I'll show you here as well that are available to you for anything you want more information on. There is a comparison between OpenFOAM applications and some other 3D CFD applications here versus HEC-RAS examples in 1D and 2D in this document that's available for you to download here. And our expert presenter today, Colin Terry, has written this article here on Entura's website, which talks a little bit about the pros and cons of approaching hydraulic structures with different models. We will talk a little bit about the difference between openfoam.org and openfoam.com, including the training page that they've got here. And again, if you would like to be kept current with the upcoming training sessions that we'll have, be sure to log on to the Australian Water School Training Hub and subscribe there. This finally, at the end, I've just got a bunch of resources here for you that cover different channels, YouTube channels, where OpenFOAM is used for hydraulic structures. You'll see spillways and dam breaches and culverts, and then some rendering. We'll talk today a little bit about Blender and a few other ways of rendering with Houdini, including this website here, where you can see a very realistic-looking waterfall. And if you look at this, you might think that's actually a real image. But if you want to see what it went into this and how this has actually been constructed, you'll see that this is entirely computer generated. So have a look here at Sky's website, which I have linked to, in addition to some of these other articles that you'll see here that Colin Terry has put together for us. And then do subscribe to any future webinars and let us know, what do you want to see more of? So with that overview of a lot of different resources that you'll have available to you, I'll stop my share. Ray, you can go ahead and start your share. And let's have a look at your screen, make sure we can see that. And then we'll turn it over to you to give us a bit of an introduction into what is 3D CFD modeling all about. Looks like I can see your screen just fine. We pull that into full screen mode. There it is. Perfect. So we'll turn it over to you. The other presenters will be answering your questions in the background. Look forward to the presentation, and we'll be back with you shortly.
All right. Thank you very much, Craig. So basically for today's presentation for myself is just give you a brief introduction of what is actually the CFD can do, what is the OpenFOAM case. So just give short brief on myself. I got my PhD in the hydraulics and coastal engineering. So the topic is related to the physical and numerical modeling on the air water flows. And I was working with consulting for a few years. Then I actually moved to Perth for my current job. So the topic covering today is I will give you a brief introduction of OpenFOAM, and I will talk about the OpenFOAM code structures, and I will highlight some of the main solvers for the large scale hydraulic modeling part, which is called interFoam. Then I will give you very simple examples by using the main solvers in OpenFOAM. Then I will do a short conclusion. Okay. So what is OpenFOAM? OpenFOAM is an open field of operation and manipulation. It sounds really fancy. It's basically just like a bunch of the C++ module can model like a continuous mechanism. So that means it's not only be able to do the modeling on the fluid and also do the modeling on the solid as well. So OpenFOAM was developed in the 1980s at Imperial College, and now has been developed continuously by OpenCFD. So the things between the 2D and 3D, 2D modeling is normally based on a finite difference method, and for 3D modeling is mainly based on the final volume method. So also there are some prerequisite skills in order to run OpenFOAM. For example, you need like the basic level of the coding skill, and also the fundamental of the fluid mechanics and the computational fluid dynamic is also very important. So basically, I guess the audience have some of the audience have the background using the commercial packages. So here I highlight what's the a key difference between OpenFOAM and also the commercial packages. So in terms of the module variety, I think both OpenFOAM and the commercial package are pretty good. It's cover like air, cover water, cover like also the two-phase or three-phase flow as well. In terms of the learning difficulties, I would say like OpenFOAM has really sharp learning curve, and the commercial package is relatively easy. In terms of the source code, because the OpenFOAM is 100% open source, and is just you can have a look this source by yourself. but that is not achievable for the commercial package. For self-development as well, because it's actually open source, you can add the things in the governing equation, but it's not achieved in the commercial package. So one thing is, a few things not is driving OpenFOAM is not popular as a commercial package. It's just like all the documentation and GUI user interface. Basically, commercial package, you have like nice user menu, you have the customer services as well, but you won't find that in the in terms of when you use the OpenFOAM. And regarding the cost, OpenFOAM is free, and the commercial package you have to pay the fee probably annually. The code efficiency, I would say like commercial package is high efficiency than OpenFOAM, because like commercial package, the code is has the professional software engineer to actually maintain. Parallel computing, I would say they will do the jobs, both OpenFOAM commercial, and but the best things about the OpenFOAM is the GPU version is still on the way. I think it's going to release soon. And so if the GPU part is coming to the play, I think the computational power of the OpenFOAM will be much better than now. So all about rankings, and this ranking present my personal opinions. In short, OpenFOAM is free to download, use, and modify. Regarding to the theoretical knowledge you have to learn to operate OpenFOAM, I highly recommend this few textbook. So the first one would be Introduction to Fluid Dynamics, and the second and third one is about the computational method for fluid dynamics, and also because the OpenFOAM is based on finite volume method, and so the textbook on the finite volume method will be helpful a lot. If you're running any turbulence model, the turbulence theory is the world classic book on the turbulence flow. Just give you some a brief on the workflow. So the way OpenFOAM running is same as the way the other numerical solver for 1D, 2D hydraulic modeling running as well. You have the pre-processing, you have the modeling, you have the post-processing. For the pre-processing, it's just like the mesh, mainly the mesh generation section. The mesh generation is really important. It's actually can impact on the modeling results. So the mesh quality is the first priority in the pre-processing phase. In terms of modeling phase, the OpenFOAM offer you different the modalities. For example, you can model incompressible flow, you can model multi-phase flow, and all different solution algorithm is available for solving the Navier-Stokes equations. Also, if you want to add turbulence modeling in, they have the RANS, large eddy simulation, and even the direct numerical simulation part. For post-processing is just be mindful the OpenFOAM just like solves the code-based solver. You have to rely on the post-processing tool from the third party. So the widely used is the per review. So it's also the free package as well. Just give you a brief on the model structure. OpenFOAM models, as I mentioned, is a code-based. It basically has three folders. So you have the constant folder, you have the zero folders to define all the initial values from the fluid motion. For example, the kinematic energy, the turbulence viscosity, pressure, and others. For the constant folder, it's just like is define constant values. For example, the fluid properties. If you model the water flow, what is the water density, like something like that. You also have the turbulence module as well. For the turbulence module, is a little bit complicated to get things set up. You have the polymesh. Sorry, the polymesh is just like sorry, I forgot to mention so when you generate a mesh by the OpenFOAM utility, you will have the mesh saved in the polymesh file. Regarding to the setup in the simulation, you have the system folder. So the system folder, you have the both mesh dictionary to generate the mesh. You have the control dictionary to define the simulation time and the post-processing functionalities. You have the final volume scheme. Just that is a bunch of the numerical scheme to solve the Navier-Stokes equation. You have the final volume solution that is for the numerical solvers, smoother, and tolerances in the simulation. Basically, for today's topic, basically in order to, so the OpenFOAM is a big package. So to solving the large-scale hydraulic modeling is one part of the OpenFOAM function. It's called the OpenFOAM interFoam. interFoam is just basically solve the two incompressible Navier-Stokes equation. Two means one in the air phase, one in the water phase. So the solver uses the volume of the flume to track the free surface. I just highlight the continuity equation and the momentum equation here. For example, this value alpha is the key indicator function to actually recognize if the phase is a fluid or air. Coming to the what is the result look like? Here, just a very simple example you can find in the OpenFOAM tutorials. This is a two-dimensional dam break type flow. As you can see, this is the 2D modeling, by the way. So you have T nearly equal to 0, you have the water column. Then with the time increasing, this water column just all collapsing. You have this free surface flow, right? So that is really simple. This is part of the OpenFOAM tutorial. Coming into the 3D modeling, I think this is most of the audience would actually be interested into when they actually running their own CFD. This also comes out from the OpenFOAM tutorial. You have the 3D dam break analysis with the structure in the middle. So here, this fluid surface is a void fraction equal to 0.9. So void fraction means so at the near the free surface is mainly the pure water part up to 0.9%. Sorry, just to give you the animations to see what happens if the water column collapses into the structure. So that is a really simple simulation. It can be run in 1 or 2 minutes, and it's not considering any turbulence model. But you can see here, so the simulation can well capture the small water droplets. Yeah. If you move to the other example on the right-hand side, so basically this is like a tank. Water tank, you have the inflow coming in from the cover, you have the outflow coming out from the cover. This also the void fraction up to 0.9. You can see this simulation can well capture the flow mechanics where the flow coming to the tank, generate some the air pocket, air aeration, and there's some air aeration happen at outlet as well. Yeah. So basically, you can run this tutorial by yourself at home. This is just a part of the OpenFOAM tutorial. coming to like a really complex, not really complex, it's just like more complex model for, so basically, you probably not going to run this kind of the modelings in your consulting. This is mainly for the research purposes. And this is, so I wrote this model use large eddy simulation. So the mesh size is really small. It's 2.5 millimeter. It's using the HPC computing. HPC means the high performing computer, I think, or high performing cluster. So this is a videos like for a breaking ball. So just by the way, if you don't know breaking ball, you can just imagine it's the hydraulic jump in motion. So by large eddy simulation, you can see this cross-section view in the video. So the CFD can capture the air pocket into in the flow. Yeah, it's just you can see the capability what OpenFOAM can do is really powerful tool. So, and also in order to run this kind of the simulation, it's required a lot of computational resources. It's probably required over 100 core to run a few days for the purely 3D simulation of this breaking ball. I guess this is the from my point here. I just give you a brief introduction of what OpenFOAM can do, and they give you a brief on the for the structures and all the different modules in OpenFOAM, and I particularly highlight the modules which can do the large scale hydraulic modeling. Since that's all for me today, Craig.
Thanks. Oh, that's great to see all of those resources for you. I do get the sense from some of the comments here that this is a bit overwhelming, and we don't want to fool anybody into thinking that you're just going to open up a package like OpenFOAM and just install like a regular Windows program, open it up and run it, and just be able to look at results. It is a little bit more complicated than that. And, our first session for our upcoming course, it's going to take several hours, I think, for everyone to get their computers up to speed in order to join the first live session. So we will have some units showing you how to do that. But it's not something that, we can step through from scratch in the very beginning in a 60-minute webinar. What happens is this webinar will become the introductory unit for that upcoming course. So, Colin, if you want to go ahead and share your screen, thanks so much for all the questions that are coming into the background. Keep those coming. Ray, you might want to answer a couple of these questions that have just come up about, 100 cores. Well, wow, do you need to do that in the cloud? So those are some great questions. We'll hit a lot of these with the live panel going forward. Colin, I can see your screen just fine. So we'll turn it over to you, step into the background, and be right back with you during the live panel discussion shortly. We'll see you then.
Thanks, Craig, and welcome everybody. And great talk, Ray. And I'll just segue from that into, I guess, some of those first steps and some of the things to think about. Now, as I mentioned in the intro, I've been doing CFD for 4 or 5 years, but involved in hydraulics in general for over 3 decades of 1D and 2D and 3D in the sense of shallow water equation modelling at Intura, where we are involved in water and sustainable energy consulting. So some of these things are a journey for everybody. And so one of the things I wanted to touch on is some of those stepping stones that people do from wherever they are now, and how do they get to that next step if they're interested in doing CFD. What does that mean, and what does it mean in terms of their current experience? And so one of the things we often have in Australian water school is lots of discussion around 1D and 2D modelling, and we have lots of excellent presentations from 2Flow and other modelling softwares, and some of the experience that people listening today will have is in those 1D and 2D. We saw from the opening poll that there's a number of people who are into 2D modelling as well. And so that's those experiences that you've got relevant, and understanding hydraulics, and when you're moving like I have into doing CFD, then the basic understanding of hydraulics is important. And because you're still solving the same problems about water, you're interested in water and you want to know what it does in different situations and the things it interacts with in terms of hydraulic structures. So the models that you've been using, the skills you've developed are still relevant. And as one of the questions Craig mentioned is it's a whole new language with CFD. Well, that's true in some regards, but it's still talking about momentum. It's still talking about continuity equations, and it's a different numerical system. So the differences in terms of going from a 2D model or a 3D, semi-3D, where we've got the assumptions, shallow water assumptions, where there's a hydrostatic pressure, is that with the 3D model, we're able to solve pressure as an independent variable and opens up the opportunities of water moving in vertical directions with vertical momentum, which is not something that the other models have. So these are some pictures there of the meshing systems, which are the basic computational elements behind these models, and they are, as Ray said, the basic elements of pre-processing. So getting a geometry of the problem you're solving in a right form and the mechanics of that, and then turning that geometry into something a computer can understand is the first step of the pre-processing. And that mesh for the 2D ones and the 3D ones are looking down just in a plan view. But when you look in a 3D model, the elements are not the same in all directions. And so here's a picture of a typical problem that I might be solving with flow over a dam spillway. And what you can see there on the right-hand side there is the full geometry. And the thing that's interesting is we start off with the structure and the area, the computational domain, and there's problems for most civil engineering applications, is what's generally the air or water space around the structure. You're interested in how the fluid interacts with the structure. So in that regard, the mesh fills up the space around the structure. And when we look at the detail of that mesh on the left-hand side there, we look at a particular part of that mesh in the top left there, you can see that the shapes that we try to make, the volumes, these computational mesh elements, are cubic by nature and sometimes distorted cubes as they try and fit to the shape of the structure as part of that meshing process. So the meshing system that OpenFOAM uses is kind of a bunch of cubes like Lego, and then they are onto or fitted to structures, snapped onto the structure to give it more detail where you might be interested in in this case here, I haven't also shown, which is the inflation layers, which we put right near the surface of the structure if we're interested in the skin friction as well, to try and capture where things are moving quickly. And so when you have water moving around a structure, it doesn't move right at the very skin of the structure, and then there's a velocity profile in that regard, and you want to try and capture the mesh in those areas. Now, something Ray's touched on, but I'll talk about in another way, but it's a similar question about the workflow that we have and the basics of how we go from an idea about modelling something into something which we can all see as a picture on the screen, or our clients or our stakeholders can understand. And there's a workflow which has OpenFOAM at the centre as the computational engine. To get to run the model, run the solver, we're going to need to have some geometry. And in my workflow, I generally use, it might be that structure might have come from a surveyor, or it might have come from a designer, or you may have generated that yourself. And generally, I would use some software like Blender, which is also used for looking at some of the output, but it's also useful for generating and manipulating geometry and getting your boundary conditions into the right form that you might need. So useful utility tool. And so because you're dealing with pieces of code in terms of text, you're dealing with text editors, so you might use something like Notepad++. And so using those two pieces of software, which are also happen to be free like OpenFOAM, you can generate the inputs that you might need and then run one of the solvers in OpenFOAM. And as Ray mentioned, interFoam is one of the most common ones for civil engineering applications, which I often use, where you're dealing with air and water, and it's a multi-phase flow. So create your inputs, generate your geometry, and then mesh that to create the mesh, run the solver, and then you're looking and analysing, post-processing that in another piece of software. ParaView is a very popular one, also a free piece of software. And you may also take that and ray trace it and do other more fancy things with it in Blender, and then you can generate that into YouTube, or you can send it in your PowerPoint presentations or look at it as you want. So this flow, like all modelling processes, is iterative, and I guess the heart of all of it is that mesh, and that's the most important thing to get right. And to start, we talked also that there was two sort of main flavours of OpenFOAM. There's a .com and a .org version, very similar in their syntax. There's just some minor differences in the approaches, but either of them are equally capable with some different sort of versions of some of their solvers, and so it's worth having a look at both those. And there's works on three main operating systems, although it is basically a Linux-based system. It's with Dockers and other ways around that. You can work it on Windows, natively on Linux, or on Mac OS as well. So there's some options there depending on what flavour of infrastructure that you deal with. So that's the basics anyway of starting, going around and iterating in terms of your modelling process. So the next steps, I guess, for anybody, if you're interested, is being curious about water, and in particular is the main fluid that I deal with. And when you're running models, you need to know that they are doing the right thing. And so I would recommend trying to model things. There's a lot of test cases in OpenFOAM. There's lots of good tutorials, and some of those are things you might be familiar with, and so you can run those if you are aware. But the other thing that is very useful is modelling things that you know what the answer already is, so you know whether then the software is doing the right thing. And here's an example of something I'm familiar with, is pouring some milk out of a carton and seeing if I can get into the glass or not. But here's an example of something I know what the answer should be, and so I'm able to model it, and it tells me whether I've got the right answer or not. So with all engineering problems, it's always handy to know what the answer is roughly before you start, and so then you can work towards using the model as a tool to help work out whether if I have a hole in my carton, whether that's going to the milk's going to come out faster, or it's going to glug or not into the glass or not. So these are some examples of things that you can do with OpenFOAM. And with that, Craig, I guess we probably open up the panel discussion, and we can talk about some other things, maybe some questions that people have been asking on the chat line.
Great. Thanks for that. That's impressive to see those animations in the end. What we'll do is we'll give you a chance to have a look at what's come in during your presentation, and we'll kick off with Kyle with a couple of questions, I think. There are a lot of Australians online, Kyle, and I know there are some recent guideline updates that I don't know if it's a recommendation, it's not necessarily a requirement. Do you foresee more CFD use given some of the updated guidance that's come along? And if so, say you're doing a floodway model or something like that, how much extra time should a consultant count on to be able to check things and maybe calibrate their coefficients, their losses, and things like that using a CFD model? So two questions for you.
Yep. I just pulled up the guideline as you were talking. So TMR's just updated their hydrologic and hydraulic modeling guideline, and the section here that they've added as of...
Do you want to share that? You can go ahead and share that if you want.
So. I might just paste it in the chat.
Oh, okay, great. So that'll be in the chat line. We'll put that in the show notes for the YouTube link as well.
Yeah, they've said, and I think it's awesome that TMR's taken the front foot on this. Someone had to eventually, because consultants tend to keep this stuff to themselves. Looking at all of you consultants, but they said modeling must be considered for complex bridge situations that cannot adequately be assessed by published existing bridge loss estimation methods. So they've basically recognized that there's limitations to the charts and the equations that we use to date. And I guess in Queensland, we've had a lot of floods in the last few years, which means lots of flood-affected properties, potential loss of life, damages. Like, it's basically been a disaster for a few years. So they've recognized we should probably be doing better as in an industry as a whole. So they put that recommendation in. And quite a few of their projects, I know there was that Bruce Highway job that was shared by Flow3D, someone recently has been in a few conferences. So quite a few of their projects where they've recognized it's a major waterway crossing, and there will be affluxes. You can't avoid affluxes. You can open up the crossing, impact downstream more, or you can block it and impact upstream more. Doing that extra level of modeling, it provides much better certainty. So once you undertake the CFD assessment, you start to understand those horseshoe vortices more at piers and how that might affect form losses, that contraction and expansion effects, all of that. I really like CFD for looking at those bed shear stresses and velocities and actually getting a better understanding of how much scour protection you need. I'm still not quite comfortable using the that dynamic scour solver that Flow3D was sharing not too long ago. Very computationally time consuming. I'll get to that part of the question in a sec, Gray. Very time consuming, and the results still carry that what is the HECRAS limitations in the 1D non-bound like soils type of thing. So the binding properties of the soils and those effects, it still doesn't consider properly either. So it doesn't make sense to try and model that scour depth dynamically, but understanding where your scour protection should go, that's great, because when a bridge gets overtopped, it might undercut on the downstream end and work its way on the upstream side. And even if you have concrete, it might fail at a joint and the whole thing unravels. Lots of different failure modes you can understand a whole lot better. But onto the time-consuming part, we'll go back to Kyle a decade ago trying to model bridge scour and audit some failures. This was back before there was better guidance, and I don't think the guidance has improved a whole lot for OpenFOAM and the free stuff. But back then, starting from scratch, I didn't come from a research space. It took about 6 months to actually get my first mesh into OpenFOAM and running. And I was looking at those great YouTube videos, Tobias Holzman and a few others. Even watching those videos and going, okay, I'm going to try to replicate this bridge failure. Like, that was 6 months. And lots of tears, not a lot of support from the consultancy I was working at the time. So a lot of your own research goes into it. Quite traumatic. But I got there at the end and I managed to replicate the failure. So like the outcomes were really good. And like some of the engineers have been training up in this, just going on that journey ends up like helping you grow as an engineer as well, because you start to learn to read literature better, understand limitations of all the modeling you're doing, and like you start to become a subject matter expert, or you start growing a whole lot more. Well, the modeling we do is just, what do you call it? We, especially in the consulting space, we point to a guideline and go, we've used TMR's chart and it recommends this, here's your rock protection, like here's a standard drawing that says your rock goes here, it's fine, type of thing. And if anything fails, we go, well, we use TMR's spec, like not on us. But that's not good engineering practice. Like once you start to look at all the underlying assumptions of the 1D, 2D, like Terry was touching on, you start doing the CFD or even reading the literature, maybe you can start dialing those rock sizes back, or maybe you can recognize like this failure mode is particularly important and we need to add an extra bit of safety factor or something.
Yeah.
So as you grow as an engineer and it's time.
Yeah, and I think I saw a bunch of emojis come out there. When you said 6 months, all of a sudden a bunch of people said, "Oh no!" The astonishing emoji came out there,
Sure.
and I think
that at 6 months,
a bit of a surprise.
There wasn't anything online, so I was actually, I don't know if Terry will laugh, but I was actually modeling inside the bridge, not the domain around the bridge. I'm like, why is this not working? Why?
I have done the same.
Modeling, inside the bridge. And
I have done the same. I just I should have actually create a mesh for from outside, but I create a mesh inside.
Yeah.
And those pitfalls, that's exactly why we're doing this this training coming up, is because of the things that, lessons we've learned along the way. We don't want everybody to have to stub their toes the same way, perhaps some of us have when we've tried to start this from scratch. And so we want to give you some specific examples. It'll be a very simple weir, a very simple culvert, and perhaps a very simple bridge pier example, with an obstruction, potentially built on some of the OpenFOAM tutorials that are already available for you out there, and get you through the whole process. Otherwise people might look at it and you can quickly get intimidated and say, you know what, I'm going back to 1D or 2D and I'm just not going to see this one through.
And to touch quickly on the commercial as well.
Sure, yeah, there are lots of questions have come up on that.
I like Flow 3D mainly because of the user support. So on the commercial side, you're spending maybe tens of thousands every few months to run the software. So that user support's actually really important. And the commercial side, it streamlines mainly the meshing and the inputs you need in the solver. So if you dive into OpenFOAM, it's really hard to find, do I use interFoam? Do I need air entrainment? Do I need this and this? At least you can quickly press the buttons in the commercial side you need, and maybe reference a few papers and streamline the process. So at least today, you're saving weeks or months of your time doing the commercial side of things, but it costs a lot as well. So in the past, I've done a lot of these fishways. I've lost out on fishway projects because the software was too expensive. The software cost more than the engineering. So, we couldn't use CFD, which meant probably a worse outcome for the project. But there's, hopefully with what AWS is doing, the free stuff will be much more user-friendly. And as soon as you can start reducing those timelines from getting your geometry together to getting your results and referencing your literature, if you can streamline that, then, things will start, or maybe the industry will start opening up a whole lot more. Those smaller projects will be more viable.
I think the aim is, I guess, that the EFT should just be another tool in your toolkit. Like we have Excel, or we have TwoFlow, we have HECRAS, or all these things are things that engineers use, and reducing the barriers to entry for people to use the right tool for the job is important, because, as you say, if we use the wrong tool for the job, you're not going to get the right answer. And even though you might have used a guideline, as engineers, we need to be using whatever contemporary best practice is. And I think it's great that some of the authorities are starting to recognise that the opportunities for high computing are more available, and so some of the barriers are coming down. And so high performance computing is cheaper, and we just need to all skill up a little bit, but it can be a bit of a journey. And for mine, it's, as you say, Kyle, it's a good personal growth in terms of your basic understanding of hydraulics. And I'm always going back to opening up the old textbooks, and that's a common thing that I haven't sort of left behind. Even though you might be using more complicated software, it's still all about the basics, and trying to understand what you're actually looking at is very important.
Yeah, no, that's a great point. I think, and what we want to do here at the Australian Water School is to make sure that we've provided, a full spectrum of possible routes that you might want to go down. We're not going to point to anybody. I think a lot of questions have come up. Oh, is this better or is this better? There are pros and cons of everything, and depending on your organization, you may go one direction versus another. It'd be hard for a sole trader to justify with small individual lot scale projects getting into a commercial CFD program. But if you work for a large consultancy that already has licenses, or if you're looking to get beyond what you can do with the open source software, then we certainly want to point people in that direction and let them know that there are resources available. And we'll provide training resources for the commercial software as well as for the open source software. Ray, if you wanted to just have a look at any of the questions that you've answered a ton of these questions in the background, so thanks for that. Yeah. Those watching the YouTube recording will not see the actual transcript. We may link to it, but maybe if you wanted to just highlight one or two of the questions that you've answered over the course of the webinar today, and maybe focus on the ones that have been upvoted the most, and just let us know, what you want to share with the audience today.
Yeah, so I guess the lots of questions has been asked is regarding to if the package, if the OpenFOAM can do that, if the package can do this or that. So my answer is OpenFOAM is really comprehensive. it can solve not every, it can solve the most of the fluid problem, from the incompressible to compressible to like a single phase flow to like two phase flow. It can solve like all kind of the fluid mechanics questions. And also in the question, people ask like, how does that compare to the commercial packages? I would say like, I think if you have a commercial package license, I highly recommend, because it's just like you have the license, it's easy to use, and you have the really good customer support as well. As Carl mentioned, you can just like ask your questions rather than spend like hours online to try to get the thing. So I actually had a case like I have a question. I had the code wrong for one line. I spent like a few days. It's really common for these free packages. It's just like you have to run everything by your own.
Yeah.
Yeah.
Exactly. So that, and watch out for some of those pitfalls. I think I've seen some of that come up in the comments. Colin, same question to you then. The things that you've been answering in the background, what's the most relevant? We got about 10 minutes to go here. What's the most relevant information that we would want to get across to those wanting to dive into this field?
People are interested in what's the right tool for the job. So there's some good questions. People are asking about, can I use OpenFOAM for this application, or is it can it do 1D? And some of the questions are trying to understand the limitations of it, which are good. And I guess my general advice on CFD is it's really good for what I call object scale modeling. An object might be as small as a drink bottle, or it might be a dam, but it's not as good for landscape scale modeling. So the computational power required means that you're generally solving problems around a object scale solving situation. And if you want to solve a landscape flooding or a whole ocean or something like that, you're probably having a different modeling approach. So using the right tool for the job, I think, is important, and understanding the pros and cons of the different limitations. So here's a good example. You've got there, Cray, of a breach coming down for a dam, but in the model, in some of these models, some of the software, they can switch between 3D and 2D mode as well, and so that you might have some parts of your model in 3D and other parts you might simplify into 2D. But generally, what you can see is that the scale of the solving domain is around a particular object or a detail of one particular thing, because they take a lot of computing power, and you're breaking the thing down into more elements than you would obviously with a 2D or a 1D problem. And so even with access to high performance computing, there are going to be some limitations of the practicalities of time and money for those sorts of things.
Yeah, and I'll just have these running in the background. This is from a webinar we did, just a premium webinar last month, where we talked about 1D versus 2D versus 3D and dam breach modeling. So it's getting to be a little different, than some of the previous advice, which you might still see published out there, saying, oh, you can only use 3D at the actual structure, and then you'll have to couple it with 1D or 2D, anywhere when you get beyond the immediate range of it. Computational power and software and hardware, abilities have been increasing, and it is possible to run something larger in 3D. It takes a lot of resources to do it, and there are some limitations. But I also wanted to show what we're going to do next month in August. We'll be talking about tailings dams, and we will have some examples shown in Flow 3D where you can get the multi-phase, you can get non-Newtonian, you can get different layers, you can get things varying over time. But at some point, as you're moving downstream, it probably makes sense at some point to couple it with another model, put that flow hydrograph in as your boundary condition, and then just couple it with a different model, because you're not gaining anything by having the CFD at that point. Once depth averaging comes into play, then you may be all right. So I'll show you just this one right here then, if you wanted to register for that and find out a little more about tailings dam failures and multi-phase modeling and non-Newtonian type modeling. That's something that's available for you as well. So I'll go back and just have a couple of these things running in the background so that you can see some of these examples. of the CFD modeling while we're talking. Kyle, anything else that you wanted to add? Again, we got about 5 minutes to go here, so let's just highlight what we can for the group from the questions that have come in.
Two things. So the first one, a good comment from Ryan. He mentioned the USAC is developing a GUI for OpenFOAM, or they've put a tender out for that GUI to be developed. So maybe they've kind of grabbed the bull by the horns and have decided they'll make it easier on their end for the bigger user base. So I'm excited to see what will come out there. And I shared a link to Dual SP Physics. So that's in FreeCAD, and it's a relatively easy SPH solver. Still made the Stokes that smooth particle hydrodynamic solver, but it seems relatively user-friendly. But the trade-off as well, there's not a lot of documentation there either. So options exist that are out there, but it's all quite time-consuming, and you need to be committed to go down this path. The other thing quickly, the commercial software, a lot of these companies like to offer like a 1-month license if you do a online training course, or if you like do one of their webinars. So if you want to like dip your toes in, it'll be easier on the commercial side of things, and that'll save you with money. And then, once you pick up some of the fundamentals, you can then start getting into the nitty-gritty OpenFOAM side of things. So lots of options exist out there. And in hindsight, if I would do it again, I would do commercial for free for a month and learn how to mesh externally, not internally in structures.
And that's what we want to make sure that's we're not pulling away from the commercial folks and their their proprietary software that they've spent a lot of time developing. But that is true. You can you can dive into it, get a feel for it, and then at least you'll know when you've got that line and you've run the open source models. You'll know when it's time to perhaps move into another package at that point.
A lot of this stuff is very counterintuitive, at least with the free stuff, and the selling point of commercials, they streamline things and hold your hand a little bit. So, and that's not a good thing for CFD as a whole, by the way. Like, you still want to do your due diligence, and you want to do your literature reviews and have someone suitably qualified with experience overseeing things, because I've told some of my engineers, like, I can give you whatever output you want for a model. I'll dial down the fluid density, so like water levels have dropped type of thing. You can do all sorts of dodgy things to get the outcome you want. So
yeah, that can be scary. And that's one of the things we'll demonstrate next month in our tailings dam webinar. We've got an actual tailings dam breach that's been modeled in 5 different packages, and the viscosities and shear stresses that were used to calibrate to the same actual event. Everybody knows what happened. Vary sometimes by up to an order of magnitude. So it can be a bit disconcerting. And we tell people in our HEC-RAS course, it's the same thing. You can get beautiful looking results, all this particle tracing and everything else with absolutely unstable models. It is something to be very careful of and very cognizant of as a modeler. I hope we haven't intimidated people too much with some of the language, but what we'll show you, if any of this went right over your head, and as it did when I went to my very first university course, my graduate course in fluid dynamics. When I first went in there and I heard the lecture, I just thought, this isn't for me. I don't speak this language. But getting into the practical bits, again, what you do in CFD, it's got to still match the nomographs that they put together when they built full-scale models of culverts back in the 1950s. It still has to match. It still has to match physics. V squared, you still have to get, your head still has to equal V squared over 2G. You can't add energy to the system without having energy to add. These basic principles of physics are still going to have to apply. Courant numbers and things like that, computational time steps. Wow, Ray, you scared me there with a 2.5 millimeter grid space. that's tiny. Actually, the time step that you need to run
is purely small
for a model scale.
That is not for the consulting scale.
Exactly.
For the research scale.
I've models with that sort of scale, but it just takes more time.
Yeah, exactly. So closing remarks from everybody. Let's just go around the room. Let's just close it up here. We've got just a minute or two to go, and then we'll pop up some additional resources in the background while we're closing out. Let's just go back in the order that we had. Ray, then Colin, then Kyle to close it up for us. Ray, any closing remarks for today?
I think not much. I think just be mindful that in order to learn the CFD, the fluid mechanics fundamental is important. I strongly encourage people to have a look at the textbook. And I know it's hard to understand, but if you master the theoretical background, you can easily use for the other tools as well. It's not only for the OpenFOAM.
Yeah, no, perfect. Colin, final.
Just a little bit of a health warning. It can be very addictive. I find that when you get into it, especially, I find I can spend way too long and getting excited about small things and large things. But water's exciting and fluid, so this is another way of expressing that excitement, I guess. So I think it's good. It's good fun. So it can be hard, but it is definitely very rewarding as well. So it's worth pursuing.
All right, Kyle, bring it home for us.
Addictive, but I guess like drugs, you can give yourself mental health issues with. I was going to add anybody that actually invests their time and goes through the process, like it'll be tedious and long, they'll grow as an engineer, develop forward. So the time will be worth it.
Perfect. And so our point today is not to scare you away from it, but to show you that this will be a bit of a journey, and you do have resources available to you. So go back to that website, hydraschool.org/CFD, and you'll see some of the resources that we have available on the Water School channel and on the OpenFOAM websites. I hope we've given you, as much content as we can in this 1 hour. We hope you get to try this yourself, whether it's through open source or commercial software or both. We want you to have those resources, and we'll bring you more of this content as this field continues to increase in its prevalence and ease of use and time and computational power. As that improves over time, I think a lot of us are going to get into this where we might have had some barriers in the past. So with that, do let us know what you want to see more of. Thanks for attending today. We'll see you next time with the Australian Water School.